This is an introduction to volume of revolution with disks. In this video, I'll go over how to find the volume of an equation which is rotated around the y-axis or the x-axis, and we can do that using integration techniques and formal knowledge of geometric equations. And we'll be doing this using the disk method. So usually you'll get a question in this form where it asks you to find the volume of a solid after revolving an equation around the x-axis or y-axis. So the first step is to draw a graph and visualize it first. And so y equals x squared is the equation we're given. The rest are just constants, so it's not really an equation. So y equals x squared is what we're dealing with, and if you recall, y equals x squared looks something like this. Actually it looks like this. And in this case, it says it's bounded by this equation, y equals 0, and around the x-axis from x equals 0 to x equals 2. So x equals 0 is a vertical line. It's this line. And that's x equals 0. And x equals 2 is somewhere over here. X equals 2. Y equals 0 is this horizontal line. Y equals 0. And so this horizontal line is y equals 0. So what we need to find out is find the volume of the solid formed by revolving the region bounded by this equation and these bounds. So try to visualize this area bounded by all of these different lines, and this is the area we're looking for. This is the area. And what's the volume of this area once we revolve this region around the x-axis? So the x-axis is this axis, right? The horizontal axis. When you revolve this area around the x-axis, you get a conical 3D object. And so it's important to visualize revolving this region, revolve this area this way. So we're revolving it around the x-axis. So when we revolve this, you get somewhat of a conical figure. And this is 3D. Okay. And so once you visualize this, it makes the process easier. So it's a cone, but you can also call it a cylinder, right? You can use the formula for a cylinder in this case as well to find the volume of such an object, right? Because it's a cylinder. And the volume of a cylinder is, if you remember, pi r squared h. That is the volume of a cylinder. And so using this concept and this equation, if we break up this figure into infinitesimally small pieces, or in other words, integrate this, we can replace the height of this equation with dx. So dx, if you recall, we use it in an integration, is just an infinitely small piece of this figure. And so we can replace h with dx, and then if you plug in pi r squared, you can say pi, and then r in this case, what is the radius of this figure? Now again, when we revolve around the x-axis, we get something like this, right? And so the radius is this region, all of these multiple regions, right? This is the diameter, and it changes constantly. And the radius, it changes constantly as well. So the radius is always going to be this equation, y equals x squared. Because when we plug in 1, or when we plug in 0, for example, y equals 0 squared, we get 0. So at this point, this is where x equals 0. Y equals 0 there as well. So the radius is 0. And so when we increase the value of x, y increases as well. And so that is our radius. Y is our radius, right? Because if I make this figure like this is our 3D figure. If you rotate it around the x-axis, the radius is the y value. So using this information, we plug in y, which is x squared in this case. It's not 0 because 0 is a constant and we can't plug that in. So we plug in x squared. And so we have this equation we can use now. Now you might be thinking, what are the lower and upper bounds for this integral? The lower and upper bounds are given to us. It's actually from x equals 0 to x equals 2. And that's basically where the figure ends. So it starts at x equals 0 and it ends at x equals 2. And so those are our bounds. Our lower bound is 2 and our upper bound is, our lower bound is 0 and our upper bound is 2. And now from here, all we need to do is integrate. So we can put the pi outside because it's a constant. And since we're integrating, we can take any constants outside. And so we get this. Same thing. We just took the pi outside. And so now we just integrate. X squared, using the power rule, we get x cubed over 3. We have pi here. Multiply by this. And then 2, 0. And just simple definite integration. And we plug in first 2. 2 cubed is 8. So you get 8 over 3. Minus, plug in 0. 0 cubed is 0. Over 3 is 0. So 8 over 3 minus 0 is 8 over 3. And then don't forget, we need to multiply by pi. So our answer is 8 pi over 3. And so this is the volume of this figure, the volume of the solid formed by revolving the region bounded by this equation around the x-axis. Now it would be different if this was the y-axis, because then the figure would not go vertically, it would move horizontally. So it would move like this. And so this is the volume we get after integrating and finding the equation. Next question. Find the volume of the solid formed by revolving the region bounded by y equals square root of x and y equals 0 around the x-axis from x equals 0 to x equals 4. Now again, our first step is to make a graph and put down all of our equations. Now, if you recall, y equals square root of x looks something like this. And so y equals square root of x looks something like this. The other, y equals 0, again, is just this line. X equals 0 is again this vertical line. X equals 4 is 1, 2, 3, 4, this vertical line. And so this is our area, enclosed or bounded by each of these equations. This is the area we're dealing with. And it asks us to find the volume, of the solid formed by revolving this region around the x-axis. So we'll revolve this way. And so we get a figure like somewhat like this. Right? And this is a 3D figure. 3D figure. So I'll give it some depth. And so we can use our previous knowledge to now write the cylinder, the formula for the volume of a cylinder is pi r square h, and this is the volume for a cylinder. And since this is a cylindrical 3D shape, we can use this formula. And since the radius varies and r square is the radius square, we can integrate like before. So this turns into pi times the radius square, which in this case is again the equation y equals square root of x. So square root of x is r, and then we square that, and then h in this case, like I said before, h is the infinitesimally small dx's. So when you integrate an object, you split it up into infinite pieces, and so each of those pieces is called dx. And so now all you need to do is integrate this, and you can write pi times square root of x squared is just x, and then dx. And so like before, we can take pi outside and then take the integral of pi dx. Now in this case, the bounds are the same, from x equals 0 to x equals 4. Again, that's just where the 3D object starts and ends, from left to right. So then our lower bound is 0 and our upper bound is 4. So now all we need to do is evaluate this equation. And so integrating this, we get pi. Wait, no, that's not pi. That's x. This is x. Pi times x squared over 2 evaluated from 0 to 4. And so that was just power rule, x squared over 2. And so now 4 squared is 16. 16 divided by 2 is 8. And then 8 minus 0 squared over 2, which is 0. So 8 minus 0 is 0. And that gives us pi times 8, which is 8 pi. And so this is the volume of this cylindrical 3D object. The volume of the solid formed by revolving the region bounded by this equation around the x-axis. Next, find the volume of the solid formed by revolving the region bounded by y equals x cubed and y equals 0 around the x-axis from x equals 0 to x equals 1. Now, just like before, our first step is to draw a graph and input all of our equations. So y equals x cubed. If you recognize x cubed, you might need to graph it using a graphing calculator, but it looks somewhat like this. And so that's the graph of x cubed, and it's bounded by x equals 0, which is this vertical line, x equals 1, which is this vertical line, and y equals 0, which is this horizontal line. So right now it's pretty hard to see, but actually it is pretty hard to see. It's this area, this small little area in green, which I'm highlighting right now. This is the area we're talking about, because it's the area under the y equals x cubed curve, and it's bounded by y equals 0 from x equals 0 to x equals 1. So this is the area, and we're revolving this around the x-axis. So since we're revolving this around the x-axis, it moves somewhat like this. So this is the 3D object, 3D figure. So our 3D figure looks somewhat like this. Object looks somewhat like this. And so this is what we're finding the volume of. And so after you visualize this, you can write the equation. We can convert this to use our formula pi r square h, because what we're essentially doing is splitting all these up into small portions. So it's basically a cylinder, and so we can use the formula for a cylinder pi r square h, and like before, we can replace r square and h. In this case, r is x cubed. Don't forget to square it, because this is just the radius, and the radius square is what the formula asks us for. And now h we can turn into dx, because it's infinitesimally small pieces, and so dx is one of those pieces. And now all we need to do is integrate this. So pi, and if we simplify, we get x to the power of 6 times dx, and we can take pi out outside the integral sign, and we get x to the power of 6 dx. The bounds in this case are from x equals 0 to x equals 1. Again, that's just where it starts and ends from. So 0 to 1, 0 to 1. And so now all we need to do is integrate this this equation. And so the hardest part is getting this equation, and now all you need to do is solve it. So we use the power rule to get x7, x to the power of 7 over 7, evaluated from 0 to 1 times pi. And don't forget the pi, which is outside the integral sign. And so 1 to the power of 7 is 1 over 7 is 1 over 7, minus 0 to the power of 7, which is 0. 0 over 7 is 0, so 1 over 7. And so our final answer is pi times 1 over 7, or pi over 7. And so this is our volume. Pi over 7 is the volume for this solid 3D object, which we got from revolving the region bounded by this equation with these bounds. Now, similar question. Find the volume of the solid formed by revolving the region bounded by y equals x squared plus 1 and y equals 0 around the x-axis from x equals 0 to x equals 2. So like always, we'll start with the graph. And so all we need to do is figure out what the graph of x squared plus 1 looks like. And so in this case, x squared plus 1 looks something like this. And now we just input all the equations. Y equals 0 is this horizontal line. X equals 0 is this vertical line. And x equals 2 is this vertical line. And so we have a much clearer image. This is the area we're dealing with right now. And all we're doing is revolving this area around the x-axis. So we're doing it this way. And if you're revolving it around the y-axis, it would just be revolving it this way. So you need to visualize that. But in this case, we're doing it around the x-axis. So it would look something like this. And it's a 3D object. So it looks something like this. And so all we need to do is find the volume of this 3D object. And so using our previous knowledge, a cylinder is pi r square h for the volume of a cylinder, and then we can replace r with our radius, which in this case r is the distance from the curve to the x-axis, you see, because this is like a cylinder. And so in this case the radius, or the value of y, is x squared plus 1. So we can multiply this by x squared plus 1. and then square that because it's r square, and then h turns into dx, and then just integrate, take the pi outside, and you can, I would recommend just leaving this as x squared plus 1. Dx, and now all you need to do is integrate. The bounds are from x equals 2 to x equals 2. So power rule x squared plus 1. Oh, so you can't use power rule. You will need to do a u substitution in this case. And so to prevent doing a u substitution, you can actually just expand this x squared plus 1 the whole square, which is equal to x to the power of 4 plus 2x squared plus 1. So all I did was expand it, because if I didn't expand it, I would need to do a u substitution. And so that's more complicated, so I decided to expand it. And so since it's like this, we can use the power rule for each of these terms, and you get x to the power of 5 over 5 plus 2 to the power 2 times x to the power of 3 over 3 plus x, evaluated from 0 to 2, and then pi is out here. Multiply that by this, and so all we need to do now is plug in 2. 2 to the power of 5 is 32, right? And so 32 over 5, you can leave that as a fraction. 2 to the power of 3 is 8. 8 times 2 is 16. So we get, I'll make a box here, 32 over 5 plus 16 over 3 plus 2. And so if you want, you can use a calculator, and what you end up getting is a fraction, I believe, 206 over 15 times pi. So when we get this, we multiply by pi, 206 pi times 15. And so this is our volume, the volume of this solid, by revolving the region bounded by y equals x squared plus 1, and these bounds, and so this is the volume we get. Finding the volume of a revolution using the disk method is not hard once you understand how to complete it. And the first step is obviously visualizing the solid. This is always going to be a 3D solid. In this case, it looks something like this. And so you need to visualize that 3D solid, and you need to keep in mind that it's usually going to be a cylinder, because if you rotate this around the x-axis, it has a circular base and top. So you can use the formula for the volume of a cylinder, pi r squared h, and then replace r with the equation that y is equal to. So in this case, it was x squared plus 1, and so that will most likely be the radius. And you square that, and then you replace h with dx or dy. In all our practice questions, you replace it with dx because you're revolving it around the x-axis. If you revolve it around the y-axis, it would just be in terms of y. So here it tells you y equals x squared plus 1. You would have to algebraically solve for x. So in this case, y equals x squared plus 1 would be x equals square root of y minus 1. And so you would plug the square root of y minus 1 for the radius, and dx would be dy. But that's only if you're revolving around the y-axis. So in this case, it's the x-axis. And regarding the bounds in that case, x equals 0 and x equals 2 will not be the bounds. You will need to find where it starts and ends on the y-axis. So for these type of questions we were looking at the bounds from start to finish on the x-axis. But if it's revolving around the y-axis, we'll need to look at the bounds or where it starts and ends on the y-axis. And so once you understand all of that, using the disk method to find the volume of revolution is actually pretty easy.